Hello, sorry for the hiatus. School kind of hit. This is 3.1 homework. This problem set is particularly large, so I will not be going over, everything in extreme detail. So if you need any further explanation, feel free to message me on Discord. I left that in the description, and you can also email me. I also left that in the description. So let's start. Number one, does the diagram best describe a crystalline solid, a liquid, or a gas? So we can immediately rule out a gas because gases are kind of more spread out. There's less density, you know, like that. But no, they're all kind of relatively connected together, you know. But I would also say it's not a solid because there's no structure. Like you can see that like here especially or here, the density is super different. There's no like concrete structure. So I would say that it'd be a liquid because liquids are kind of still connected because there are it's kind yeah, you know what I mean. And still it is not a structure as in a solid, it's kind of amorphous, which is kind of what we see in this diagram. So for those reasons, it's a liquid. Okay, moving on. Number two, which kind of intermolecular attractive forces are shown in each case here? And predict which of the four interactions are the weakest. So this is kind of gone over in the first or second part of chapter 11. So if you struggled with this, you should probably look back on that. And I might also post a video on this chapter. I don't know yet. So for number one, or I guess I'll just say one, we see an HF and an HF. So HF, it is a hydrogen bonded molecule because the H and the F, so fluorine qualifies to be hydrogen bonded. It's the most electronegative element actually. The three elements that qualify are nitrogen, oxygen, and fluorine. I always just say NOF. I don't know, works for me. So since we see an HF and an HF, we're gonna say that it is hydrogen bonding. Okay, now for two, we have F2 and F2. Now we see that both of these molecules are, first of all, these are gases, which tells me that it's not particularly like strong intermolecular forces. But anyway, um, both of these molecules, well, they're the same molecule, but the molecule is nonpolar. That means that there's no dipole. So there's none of that. There's no dipole, and there's no hydrogen bonding because there's no hydrogen. So the only thing that's left is LDF or London dispersion forces. These are pretty weak forces, so I would say that this is qualifies for the answer to be part B. But moving on, for three, we have an Na plus ion and an H2O, I believe. Yes, an H2O. Now we know that H2O is a polar molecule, so I would say it has dipole forces. And Na plus is an ion, so just by existing, it is polar, I guess. It has those it has forces in it, I guess. So I would say for three, it'd be ion dipole forces because it's an ion and a dipole or a polar molecule. So that's what the forces are. And then for four, I think this is SO2. Now both of these are dipoles. They're very polar molecules. So this would be dipole-dipole forces because there's no ion. It's just two polar molecules. And the answer for part B is the fluorine interactions because they are not as polar, or they're not polar at all. They're just LDF forces. Okay, do you expect the viscosity of glycerol to be larger or smaller than that of 1-propanol? Explain. So viscosity is kind of an indicator for how strong intermolecular forces are. So something with very high viscosity would have very high intermolecular forces, very strong intermolecular forces, and vice versa. So it's asking us to compare the intermolecular forces and see which one's stronger, basically. So with glycerol, we see that it has three hydroxides, which are very strong, like they're very polar and they have hydrogen bonding. So that indicates a very high amount of intermolecular forces. And 1-propanol, or just propanol, has only one, which means that the strength of the intermolecular forces of glycerol is much higher, 3 times even, because there are 3 times more OH groups. And again, OH groups are very, very polar. They're very good at increasing the intermolecular forces. So for that reason, number 3 is glycerol. All right, number 9. List the 3 states of matter in order of increasing molecular disorder and increasing intermolecular attractions and by how compressible they are. I'll go through these pretty fast. So for molecular disorder, it goes solid, liquid, gas, for pretty obvious reasons, hopefully. where a gas is just the most out and about. They're all over the place. It's hard to predict. There's more energy inside of them. And a solid, they're all in a very structured form. So it's very not disordered. It's very ordered. And then for intermolecular attractions, it's the opposite, where solid has the most intermolecular attractions because of the most force connecting them together. With a gas, there's basically no forces connecting them together, as they're just freely floating on their own accord. And then with easily compressed, it's the opposite again, where gases are the most easily compressed and solids are the least easily compressed because gases have the most empty space between them, with pressure. So you could easily compress them and just increase the pressure. So yeah, that's number 9. And then for 11, arrange these substances into increasing boiling point in order of increasing boiling point. So with these questions, they're a little tricky, but you can order them based off of just what um, they are in standard, like what state they are, like in standard temperature and pressure. So with argon, since argon is a noble gas, it's going to be a gas normally, and then CCl4 is a liquid, and silicone is a solid. So yeah, that's just how it's ordered. You can also make an argument with the intermolecular forces by saying that since argon doesn't bond, or it's just on its own, or it's AR, I don't remember. But since argon is not, it doesn't form bonds really with anything. It's just out and about. It will have very low intermolecular forces. Therefore, it's a gas. It'll have low boiling point. And since CCl4 is a non-polar substance, it's going to have low intermolecular forces anyway, but it still has LDF, so that's why it has a higher boiling point than argon. And since silicone forms network covalent bonds, it's going to be more of a solid. And in general, since silicone is a metalloid or a metal, it's going to be a solid anyway. So you can visualize it however you want. And then with 12, we have gallium, neon, and bromine. So we know that, again, since neon is a noble gas, it's a gas, so it's going to be sitting on its own. And bromine is actually a liquid. It's one of the only liquids on the periodic table. So yeah, besides mercury. And gallium, I believe, is a solid. It's a metal. Yeah, it's a metalloid. So it's going to be a it's going to have the highest boiling point. And this is pretty tricky, I know, because of just this is kind of like looking at the periodic table. There's not as much of intermolecular arguments that make sense here, although you could, because bromine, it is a nonpolar, and gallium, since it's a metal, it forms network covalent bonds or metallic bonding. So therefore, it has solid and it's very strong bonds. But it's kind of hard to argue with these questions. So usually, it's better to use a periodic table or your knowledge of standard states to do these questions, but they don't really come up anyway. So yeah. All right, 17. Describe the IMF forces that must be overcome to convert these substances from a liquid to a gas. We have SO2, acetate, and hydrogen sulfide. So for SO2, since it's a polar covalent molecule, because it's polar, it's not even at all. Um, it has dipole and LDF forces, and also there's lone pairs. Sorry, that contributes to being polar. So for those reasons, it has dipole and LDF. So yeah, that's that for A. And then for B, acetate, it's polar covalent, but it also has hydrogen bonding with this OH here. So therefore, it has all three. It has LDF, dipole, and hydrogen bonding. All those forces have to be overcome before you have a liquid to gas transformation. And then for hydrogen sulfide, it is a polar covalent molecule because it's polar because of these lone pairs. Therefore, it has LDF forces and dipole forces. And then for 18, it's asking for the IMF forces that account for these differences that should or shouldn't exist, I guess, or don't make sense to some people. So for A, we have a CH3OH, which I think is methanol, and CH3SH. So it's asking, why does methanol have such a higher boiling point than CH3SH? And that's because methanol has hydrogen bonding, and hydrogen bonding greatly increases the boiling point. As you can see, there's an OH bond, a hydroxide, and as I've said before, a hydroxide greatly increases your boiling point and it greatly increases your IMF forces. So that's why. And then for B, Xenon is liquid at 8 atmospheric pressure and 120 Kelvin, whereas argon is a gas under the same conditions. So if you look on the periodic table, uh, xenon is lower, which means it's heavier. So that means xenon has more LDF or stronger LDF forces. It's more polarizable. Therefore, xenon will be liquid and argon will be a gas because argon has less force on it. With C, krypton, boils at 120.9 Kelvin, whereas chlorine with around similar molecular weight boils at 238 Kelvin. So both of these gases are nonpolar with LDF forces. However, since chlorine has two molecules, or chlorine gas, it has two molecules, it's much larger, therefore it's polarizable. So for those reasons, chlorine has a higher boiling point just because there's two molecules that are increasing the size so much. And then finally, acetone boils at 56 degrees Celsius, whereas 2-methylpropane boils at negative 12 Celsius. So again, 2-methylpropane is not polar, therefore it only has LDF forces, and acetone is polar with that double bonded oxygen in there. Therefore, acetone experiences dipole-dipole forces and has a higher boiling point by consequence. Okay, 19. What is meant by the term polarizability? This is kind of a textbook definition, but polarizability is just in general referring to the ability for a molecule to just have its electrons move around, have a larger electron cloud, and just move around and create a temporary charge, thus giving it those temporary intermolecular forces. Therefore, we see that the larger molecules or the larger atoms have higher polarizability, thus higher LDF forces. Okay, B, which of the following atoms would you expect to be most polarizable? So nitrogen, phosphorus, arsenic, and I believe tin. So tin, or Sb, is the most polarizable because it's the largest, therefore there's more electrons, and in general, the nucleus has less control over those electrons, so they're just moving around a whole lot more. And then for C, put the following molecules in order of increasing polarizability. Basically, put the following molecules in order of molecular size. So the smallest is CH4, and the greatest is germanium bromide, and you can kind of connect the dots there. All right, D, predict the order of boiling points of the substances in part C. So the magnitude of LDF forces and thus the boiling points of molecules increases as polarizability increases. Therefore, it'd be the same list because polarizability and boiling point are they go hand in hand. They're not the same thing, but they correlate very strongly. So it would be the same list. All right, 23. Butane and 2-methylpropane are depicted at the bottom right there. So they're both nonpolar and have the same molecular formula, yet butane has a higher boiling point, and just explain why. So butane, as you can see, is kind of a flat molecule, while 2-methylpropane is not, where it's just, I think, this. So the reason why butane has a much higher boiling point is because it is much easier to stack or just put things on each other that can be more densely put together. Therefore, it takes more energy to separate them because they're just so condensable. Like you can put them together so easily. Therefore, the pressure would be higher. I mean, not the pressure, the energy required would be higher. And the opposite is true for 2-methylpropane. Since it's kind of a weird shape, they're kind of more spread out. I'm not sure if this is the shape actually, but it's like something like this. It's like an odd shape. So it's kind of harder to put them together, therefore it takes less energy to make them boil or make them separate. Therefore, 2-methylpropane has a lower boiling point. All right, 34. Distinguish between adhesive forces and cohesive forces. This is kind of simple. Cohesive um, kind of bind molecules to each other, so kind of IMF forces. Adhesive forces are just connecting a molecule to a surface or to just like a anonymous non-reacting thing. So like a wall or like glass, just whatever. And then for B, what adhesive and cohesive forces are involved when a paper towel absorbs water? So the cohesive forces are the hydrogen bonding, dipole-dipole, and LDF forces that are keeping the water together, keeping them as a liquid. And the cohesive forces is the water molecules' attraction to the cellulose or just whatever is in the paper towel. And then for C, explain the cause for the U-shaped meniscus, which I crudely drew here, forming waters in a glass tube. So if you take a closer look with, like, I don't know, with a magnifying glass or just whatever, you see that the water molecules are kind of they have these cohesive, no, they have these adhesive forces actually with the silicate walls of the glass. So the water would kind of climb up the walls of the glass, kind of like zombies in The Walking Dead. Okay, sorry. So they kind of climb up because of the forces that connect them together, the adhesive forces. So yeah, that is the reason why. And then for 37, gives you a chart of the boiling point, surface tensions, and viscosities. And then for part A, for ethanol, propanol, and butanol, the boiling point, surface tensions, and viscosities all increase. What is the reason? The reason why is because ethanol is a smaller molecule than propanol, and propanol is a smaller molecule than butanol. Therefore, there are higher LDF forces that lead to higher boiling points, higher surface tensions, and higher viscosities because there's more things keeping them together. It's more polarizable, all that vocabulary. Okay, for part B, how do you explain the fact that propanol and ethylene, which is the bottom one, have similar molecular weights, yet the viscosity of ethylene is more than 10 times larger than propanol? So propanol, it just simply has a single OH group, which gives it a little bit of IMF forces, but glycol has two, I think. If I mean, and it is also a little bit more polar because it's a little bit more asymmetrical. Therefore, it is more. It has more IMF forces and it is much more viscous. It has much more IMF forces. Therefore, just in general, it is more viscous. Part C. How do you explain the fact that water has the highest surface tension but the lowest viscosity? So I was mistaken. Viscosity is more tied to the size of a molecule. It is connected to the IMF forces, but it is more connected specifically to the molecular weight. So since water has the smallest molecular weight, it's going to have the lowest viscosity. But since it is very polar, and since the whole molecule is polar, while ethanol, propanol, and butanol, and ethylene glycol is they are polar most of the time, but there's only one OH group, and that is in comparison to the huge molecules that they are. Like N-butanol has one OH group, and it's like 6 CH3s, so it's not a lot of polarity, or in comparison, or I guess in relative. So we see that water is the most polar, or has the highest surface tension, but the lowest viscosity because it has the highest surface tension because it is the most polar, and it has the lowest viscosity because it is the smallest. And that is all. Thank you, and have a good night.